Rate of reaction is defined as the change in concentration of a reactant or product per unit time. In order to measure rate, you must determine how fast a reactant is being used up or how fast a product is being produced. For example, consider a reaction where reactant A is converted to B. We could measure the concentration of reactant A over a period of time, or we could monitor the production of B over a period of time. In a typical reaction, the rate of reaction slows as the reaction proceeds, because the concentration of reactant decreases, and as a result, the collision rate between the reacting molecules decreases. In order to determine the rate of reaction, that is, the change in concentration of reactants per unit time, you first need to collect data by analysing the reactant concentration with time and then plot a graph. To find the rate at a given time, you need to find the gradient of a tangent to the curve at that time. For example, with this data, if we wanted to know what the rate of reaction was after 300 seconds, we first draw a tangent to the point at 300 seconds. To do this, you place your ruler away from the point and adjust the angle until the ruler crosses the curve at equal distances from the point. You then bring the ruler in towards the point, keeping the distances either side of the point the same. As soon as the ruler touches the point, that is the tangent to the curve. You then use this tangent as the longest side in a right-angled triangle. Generally, the larger you can draw the triangle, the more accurate the gradient calculation. You then use the scale of the graph to find the dimension of the vertical side of the triangle. For example, here, the top of the triangle equates to 0.074 moles per decimeter cubed on the reactant concentration axis, and 0.02 moles per decimeter cubed for the bottom of the triangle. The difference between these two numbers gives us the dimension of the vertical side of the triangle, which in this case is 0.054 moles per decimeter cubed. We do the same for the base of the triangle, except this time we drop lines down from where the base of the triangle starts and where it finishes, and then find the difference. We can now find the gradient of the tangent, and therefore the rate of reaction at 300 seconds, by dividing the vertical dimension of the triangle by the dimension of the base. And if we divide 0.054 moles per decimeter cubed by 520 seconds, it will tell us that the rate of reaction is 1.04 times 10 to the minus 4 moles per decimeter cubed per second. We can do the same at various points along the curve to find how the rate changes with reactant concentration. Calculating the rate of reaction at time 0 is a little tricky, but you do it in the same way. Just imagine the curve extends back from 0 time. You can also measure the rate of reaction by measuring the concentration of product formed as the reaction proceeds, and once again, find the rate by drawing tangents to the line.